we will use the method of Frobenius to find the solution for this equation. Right. The Frobenius theorem, we will let y equal to a series the regular series is like that, but for the Frobenius method, we're going to add the r into it. And then we check the derivative and the second derivative. Will be n plus r h sub n x to the n plus r minus 1. Notice that the index does not change, still from 0 to infinity. And then the second derivative. N plus r minus 1 a sub n x to n plus r minus 2. And then substitute that into the original equation. We should have 2x, the second derivative, n plus r minus 1 plus 1 minus x, the derivative, a sub n x n plus r minus 1 minus 5 a sub n x n plus r equal to 0. Notice that all of them has x to the r power, so I will factor it out, x to the r power, common factor. Inside, actually I will multiply the 2x inside, so we're going to have plus 1 into the exponent. Right. So the series will become n to 0 to infinity, n plus r minus 1 to a sub n x to the n. X to the r we factor out, and the minus 2 here with the 2x in front. So in that case, that becomes only n minus 1, because the x here to the first power, bring it inside, we only have to the x minus 1 there, right? And then we have 1 minus x, and this will stay the same, so I just copy it down. Except the r power is factored out, so we have that. I will check the 5 inside, and x to the r factor out, so we have that. Right. Next, I just multiply the 1 minus x here into that summation. That's the only thing I do on the next step. So x to the r still on the outside, and then we have summation n plus r minus 1 to a sub n x to n minus 1. Multiply by 1 itself, so that's easy. And then when I multiply x to it, minus summation n equal to 0 to infinity n plus r a sub n. Now we multiply x to it, so pretty much we'll add 1 to the power. So that becomes just x to the n power. And then we have the minus 5, and that series is unchanged. Right. Now we combine the series. Just like we combine the series, the other series, we just see where it starts. So I will check real quick. When n equal to 0 here, it will start 0 minus 1. So it's this one start at x to the negative 1 power. For here n equal to 0, this one will start at x to the negative 1 power. This one obviously starts at 0, x to 0 power, which is 1, and this one starts at the n power. X to the 0 power. So because of that, we have to split two terms out of the summation. This term that starts at x to negative 1, we have to split. So first I'm going to put n equal to 0 into it. So we have 0 plus r, 0 plus r minus 1, to a n is equal to 0, and x to the n minus 1 will be x to the minus 1. That's what we have. And then now the series will start from n equal to 1, because we write n equal to 0 already. And everything will stay the same. Right. And the next series also start x to negative 1, so we have to split out one term, n equal to 0, so we have 0 plus r, a sub 0, x to negative 1. So we split out that term, and now the series we start from 1, and everything stay the same. And the next two series is unchanged. Right. This is a very long problem. Right, next, let's just clear out a few things. Combine like terms. I'll take a look at anything that is not in the summation. So we have all that and all this here. So we have r times r minus 1 to a naught x to negative 1 plus r a naught x to negative 1. So those two terms are not in the summation. And then we have the summation. Right. Now on the summation, now we start x to the 0 power, which is good. So the first one, in this case, we need to make the adjustment. We will match that to x to the k. So in that case, we say n minus 1 is equal to k. So n is equal to k plus 1. So we're going to make that adjustment. The series now in terms of k. Now if n is equal to 1, we say k plus 1 equal to 1. So k will start from 0 to infinity. And we have n plus r, but n is k plus 1. So we have k plus 1 plus r. And then k plus 1 plus r minus 1. So that will be just k plus r. 2 a of n is k plus 1. X is to the k power. So we'll make that adjustment. Right. The next series here, we also need to make the adjustment to x to the k. So n plus 1 is equal to k. Sorry, n minus 1 is equal to k. So n is k plus 1. So we have the summation k equal to 0 to infinity. N is k plus 1 plus r. N is k plus 1 x to the k. Right. And the next we have the two series at the second line. All we need to do is turn k into n. So k go to 0 to infinity. K plus r. A of k x to the k. For those two series at the bottom, we just take n equal to k. And we don't have to do much. A to the k x to the k equal to 0. Right. Now the first part, let's factor out the a naught x to the negative. X to the r is on the outside. And the first part we will factor out a naught x to the negative 1. Inside we should have 2r minus 1 plus r. And then now we combine the series. Right, first we can only factor out x to the k. So first we have k plus 1 plus r, k plus r to a k plus 1. That's the first coefficient. X to the k factor out. Next we have k plus 1 plus r, a to k plus 1, k plus 1, and then k plus r, a sub k. Try to fit everything here. Minus 5, a sub k, x to the k. And we still have closed the curly bracket equal to 0. Right. Right. So it's almost correct. I'll just need to fix this. This will be a minus because I just copied it from here. That should be still that. Right. The next step is, since the right hand side is equal to 0, that means all the coefficient here has to be equal to 0, and everything in here has to be equal to 0. All the coefficient has to be equal to 0. So from that we have two parts here. Two things has to happen. first, the equation in black, we have 2r squared minus 2r plus r, so minus r equal to 0. That first thing have to happen. By the way, that is the initial equation. And then the second part in blue has to be equal to 0. And see if we can simplify anything here. So first, the a of look like we can factor out a to the k plus 1 here with this, a to the k plus 1 here with that. So I factor out the common factor of a to the k plus 1 of k plus 1 plus r. Inside, then we just have, don't forget there's a 2 here. So 2k plus 2r and then plus 1. 1 will be just for this factor. So that's the first two terms. The next two terms, there's ak in common. So we will factor it out. Minus ak. And then we have k plus r plus 5. Notice the factor out the minus as well. So k plus r plus 5. That has to be equal to 0 as well. Right. The top equation, the initial equation, that gives us r, factor out an r. We have 2r minus 1 equal to 0. So r equal to 0 or r equal to 1. Each one of them will give 1/2, sorry. Each one of them will give a unique, a different solution. I'll focus on only the x to the 1/2 here. The other solution will be similar. But again, now we focus on r equal to 1/2. Now we have to go to the next page because we run out of space here. Again, r equal to 1/2. And then we're going to use this second part of the equation to find the coefficients. All right, so next page. First thing first, k is equal, r is equal to 1/2. Right, next we will rewrite the coefficient. Let me just copy that down real quick. k plus 1, k plus r plus 1, 2k, 2r, and 1, minus k, k plus r plus 5 equal to 0. With this, we can solve for a of k plus 1 equal to we move the a to the k to the other side. We have k plus r plus 5 a sub k. The bottom is just k plus 1 plus r, or k plus r plus 1. And 2k plus 2r plus 1. Which pretty much exactly we copy from the last line here. And so for a of k plus 1. Right. Now we just use some values for k. If we choose k equal to 0, and again we still have r equal to 1/2. When r equal to 0, there will be another solution. But we focus on this one only. That's a long problem already. So we put 1 in for k, 0 for k. So 0 plus 1. So that's just a1. On the top, k is 0, so we have 0. R is 1/2 plus 5 times a sub 0. The bottom is 0 plus R plus 1, 2 times 0 plus 2 times 1/2 plus 1. Now if we simplify, we will have on the top 5 plus 1/2, so it just say 11 over 2 a naught. The bottom is 3/2 and 2 times 2. So that gives us divide by 3 at the bottom, so give us 11 over 6 a naught. Right, so that k equal to 0. Now choose k equal to 1. So a of k is 1 plus 1. By the way, let's just say a1 is equal to 11 over 6 a naught. Next, a of now k is 1, so I skipped a few steps here, and then we say just k of a of 2 equal to we're not skipping any step. K is 1, so we have 1, 1/2, and then 5 a to the 1, a of 1. And then the bottom, k is 1, r is 1/2, k is 1, r is 1/2, right? Let's do the math here. We should have 13 over 20 a1. I skipped that step. And a1 is 11 over 6, so we have 13 over 20, 11 over 6. So we have 143. Oh, forgot the a naught. 143 over 120 a naught. So we have a1, and that is a2. And we only need one more term, a3. So that gives us a0, a1, a2, and a3. Let's just do one more. K equal to 2. A3 equal to right. K equal to 2, R is 1/2. K equal to 2. K is 2, 1/2, 2, 2 times 1/2, and 1. And if we do that, we should have 5 over 14 a2, and 5 over 14 a2 is 143 over 120 a naught. 5 and 120, that will be 24. The other way, 24 at the bottom, I'm sorry. And when we multiply it out, it will be 143 over 336 a naught. Right. Again, that's just one solution. So we can write a solution as follows: y equal to x to the 1/2 a naught a1x a2x squared a3x cubed which is x to the 1/2. A0 is A0. A1 is 11/6 x. A2 143/120 x squared. A3 143/336 x cubed. And then if I multiply the x to the 1/2 inside, I forgot all of them have the A0. Right. All of them have A0, and all of them have x to the 1/2. So I multiply the x to the 1/2 inside and factor out A0. So we have x to the 1/2, 11/6, x to the 3/2, 143/120, x to the 5/2, and 143/336, x to the 7/2, and the series goes on. Right. Let me zoom out to see the whole problem. Right. Right. So again, it's just a long problem. We just write a series for y, y prime, and double prime, substitute into the equation. I'll combine the series. That part is the same, but just a few things that we notice. First of all, that x to the r in common, that we factor out, and at the end we will have x to the r at the end. And then when we combine with, that's just like when we combine the regular series. And then we do have the initial equation. To that equation, the initial equation. And we find for r. There's two values for r here, but I only use one value of r equal to 1/2 to write the solution. And then we substitute in recursively, we can find all the coefficients in terms of A0. And then we can write all of them in terms of A0. And then factor it out, and then we should have the solution.